Okay, great. I'm very happy to be presenting to you. Sorry I couldn't be there in person. Uh, Greetings from Philadelphia. All is well. And I want to talk about a kind of a new approach. I know that a lot of you may remember that I used to do the kind of work that Eve and Chalmay did or showed in the first day. And that was really when I was working at ISI, and I was there with Gene Garfield for roughly 40 years. But I'm into something a little bit different now. And I'm so happy that Andrea showed the essays of an information scientist. I was just looking at that the other day to find some obscure bibliographic reference. And Gene had a unique, just speaking a little bit on off on the tangent here, he had a unique approach to evaluation. His approach was, I would call it flattery. He would create these things such as the essays or the citation classics. And if you had a paper that was highly cited in some journal, he would invite you to submit an essay in which you could, discuss your career and your history and why you did what you did and what it means and so forth. And he literally published thousands of these things, but people were really, really flattered by that invitation. And when I traveled with him anywhere, in the world, in Europe, people would come up to him and thank him. Oh, thank you, Dr. Garfield, for featuring my article. It meant so much to me. So I just want to point out that in our zeal to evaluate, we don't want to forget about complimenting people as well on their achievements. And that was what he really perfected in his life. And that's why it was never a backlash on the citation index. So now I have to make a segue to something entirely different. I got interested in Bayesian ideas a few years ago and thought that, well, maybe I should try to apply this. My background is actually in the history of science. And my first job in the history of science was at the Center for History and Philosophy of Physics. And recently, one person said, hey, there was never such a thing as a Center for History and Philosophy of Physics. It was just the history of physics. And I said, no, I'm sorry. I have the letterhead that proves that it was the history and philosophy. And this is in the late 60s and early 70s. And we went to philosophy conferences. I remember some in Minnesota that we went to. We had a wonderful library called the Niels Bohr Library, which still exists, not in New York anymore, but in Maryland. And I got to meet a lot of philosophers of science and was very impressed with the combination of philosophy and history of science. And in a way, I'm coming back to that now, kind of a little bit late in my career, so I can't get a whole lot done in the time that's been allotted to me. But I think you will find, and I will mention at the very end, some connections to bibliometrics that I see, so that we can actually possibly make a synthesis of philosophy and history of science and information science as well. So here are some of my questions. First of all, can we apply Bayesian statistics to the history of science? And in a way, this is a question has already been answered. There have been many attempts to do case studies using Bayesian ideas. And I'm in touch now with someone who's pioneered in these, named Alan Franklin in Colorado, and he had a good colleague of his who passed away named Colin Housen, somebody who you may know of. And I should also mention right at the outset that right there at Turin, you have an outstanding Bayesian philosopher of science named Jan Sprenger, who wrote a book with Stefan Hartmann called Bayesian Philosophy of Science. So right in your backyard, and I'm not telling anything to you that you don't already know, just understanding their work. But my interest is very practical and, well, not practical, but at least applied. I'm not here to talk about how you justify the probability axioms or the Bayesian formula or anything else. But you'll see where I'm going with this in a minute. So my next question is, can we estimate the conditional probability of evidence given a theory from historical accounts? And to me, this has been the big stumbling block in trying to apply in a more thorough way, in a more comprehensive way, Bayesian ideas to history of science accounts. So another question that I have is, are scientific theories analogous to communication systems? I'm an information scientist, somewhat, although I was trained as a historian. And information theory, and I believe that Chao-Mei Chen mentioned this in his talk, they use the ideas like entropy, which seem to me very interesting from a standpoint of history of science. Why? Because I think that science is engaged in an entropy reducing effort. We want to unify things. We want to see things consilient with one another. You may have heard the word consilience. It comes from William Whewell in the 19th century, and more recently, Ed Wilson, the ant guy at Harvard who passed away, he wrote a book called Inconsilience, and that's the joining together of data and information and theory. So I believe that we need to make a connection here to information theory as well as to Bayesian concepts, as well as history of science. So this is kind of an interdisciplinary mix. Now, in Bayesian work, it's usually considered to be a personalist approach. In other words, it's your personal probabilities that some theory is correct or some piece of evidence is correct. But we need, in order to apply this in any realistic way to the history of science, we need to move to a group or collective perspective. Now, I have done a couple of previous case studies, one on Watson and Crick doing their work on DNA, and also Guillemin and Shalley. I used that example that I picked up from Latour and Woolgar's book called Laboratory Life, which everybody knows about. It's a famous book. And I thought, well, let me attempt to do Bayesian analysis of the work that Guillemin and Shalley did on finding the hormone releasing factor. And that's what I did in that case study. So now I'm going to turn to one of a case study in geology that a lot of people have done historical research on, even philosophy research, namely the continental drift controversy. I want to just also say that I'm going to need to attack a failure in science as well as a success. The ones I've done, everybody got a Nobel Prize. Well, not continental drift. The fellow who should have gotten a Nobel Prize there died, froze to death in Greenland, so he couldn't get a Nobel Prize. But the Guillemin and Shalley, and of course Watson and Crick, everybody got it. So that's a success story. I want to get now, and I may do something like cold fusion or N-rays or something of that nature that we have a lot of information about. So what is my motivation, or why am I using the Bayes framework anyway? So I saw initially an analogy of theories in science to diseases in medicine. Now, what do I mean? You go to a doctor and you have a cough, you have a fever, maybe you took a COVID test. And these are pieces of evidence. The doctor is trying to decide what theory he should apply to you. Do you have COVID? Do you have pneumonia? Do you have a common cold? What is it? So there are this little figure that I have here with the theory in the middle and the evidence around it, and arrows going out to the evidence. That's one of the likelihoods that's involved in making an inference. It's the probability that the evidence, given the theory, has a certain value. And if you have a COVID test, that's pretty strong evidence. So you're trying to go from a disease, which is I'm calling an analogy to a theory, to symptoms, which is analogous to what the Bayesians call evidence. And this is a nice, simple solution. It's called a naive Bayes model. It estimates, or it gives you the posterior probability very simply. And if you want to read about that, you can go to this wonderful book called Probabilistic Graph Models by Kohler and Friedman. And when I read this book, I saw how beautifully this theory works. And the only caveat here, as your little evidence things have to be conditionally independent. Well, what's conditional independence? That means that the cough, let's say if E2 is the cough and E3 is the fever, well, the cough can't cause the fever, and the fever can't cause, but they can have a common cause, which is the disease, whatever it is. Is it COVID? Is it pneumonia? What? So the conditional independence is very important. And from this little graph, this is called a DAG, a DAG, directed acyclic graph. There's no cycles in here. So you can create this chain rule that goes from the joint probability of the theory, all the pieces of evidence, and just pick out certain dependencies, which are the prior probability PT and the conditional probabilities of the evidence giving the theory. And that's all you need to calculate the posterior probability, which is the probability of the disease given the evidence at hand. So that's my just some quick kind of ridiculous definitions here. T, I'm saying, is a theory. It could be hypothesis, a belief. Theories can be very, very elaborate with all sorts of equations, assumptions, and sub-assumptions, or they can be just simply, I believe something, a mental construct. Trump will be elected president, God forbid. Now the not T, when you put the little squiggle in front of the T, that's not T. That's the sometimes referred to as the catch-all hypothesis, an alternate theory or theories. In this case, somebody else will be elected, some other candidate. You can't. The notion that you can't have two presidents at the same time is when you get to the probability of T, the prior probability of the hypothesis, it's a number between 0 and 1, but in order to calculate the inverse of that, or not T, you have to subtract the prior probability from 1. So all the different hypotheses and their prior probabilities have to add up to 1. Then you have in the third sec here the very important conditional probabilities. the probability of the evidence given the theory. So assuming some theory is true, what's the probability of the evidence that's going to follow from it? That in some sense the theory causes, well, you don't want to talk about causality, but you want to say you can explain the evidence, you can predict the evidence, you can understand it. There's got to be some connection between the theory and the evidence. So if Trump is elected, the US will leave NATO. That's kind of a prediction. And down here we have, if if Trump is not elected, and you'll get some other result. So I'm putting that squiggle in front of the evidence. And the evidence is that US will stay in NATO if Biden is elected. So there you have an explanation, kind of a silly one, of what the conditional probability is. And finally, you have the posterior probability of the theory given the evidence. That's what you want to work out to be as high as possible if you want the theory to be correct. If you want it to be incorrect, you don't want it to be high. And you get confirmation if the posterior is greater than the prior. So when I first looked into the Bayes' theorem, I said, I got to be able to see this in order to understand it. So here at the top, you have what is called the third form. I'm getting this from a book that I called, well, it was by Houston and Urbach. It's kind of one of the classic books on Bayesian analysis. And this is what they call their third form of Bayes' theorem. And I plotted 3 different versions of that by assuming different prior probabilities. And each prior probability gives you a different surface in a 3-dimensional grid. On the horizontal plane, you have the likelihoods plotted. That is the probability of the theory given the evidence, or probability of evidence given the theory is not true. And here's the probability of it given the theory is true. And on the vertical axis is posterior. And so you can see if you're down here, if you start with a prior of 0.1, which is rather low, you're close to 0, you got a long way to go to a posterior of 1. On the other hand, if you start out really high with a high prior probability, you got a long way to go down. Now, what happens when you make, I didn't include 0 or 1 in my first plot there, but here I include it. As the likelihood of evidence given the theory goes to 0, the posterior goes to 0. It's like collapses, and it goes all the way down. And so T, or the theory, must be disconfirmed. And in contrast, as the other likelihood, the evidence given the theory is not true, as that goes to 0, the posterior goes to 1 because there's no competition. So that points out the fact that you really need to have Bayes' theorem work at all. You have to have competition. You have to have a competing theory. So in a way, this is ideal for situations like paradigm changes, where you go from one theory to another theory. And you can put them into competition with one another and see how well each of them explains the evidence. Now, this is my last diagram here. I'm going to go drive you crazy with these Bayesian sheets, I call them. This is assuming prior is 0.5. You get this nice sheet, and the dark side is the disconfirmation, and the lighter side is the confirmation. Now, why is it confirming? It's because this little likelihood down here is bigger than this one, and therefore you get a confirmation. If in the other sense, if this is smaller than the other likelihood, you're going to get disconfirmation. That just embodies the idea that if this likelihood ratio, the ratio between these likelihoods, is greater than 1, then the posterior is going to be greater than the prior and theory is confirmed. If, on the other hand, they're equal to one another, which is this black line, then you're not going to get any confirmation at all. The prior and the posterior will be exactly equal. Now, in order to make a connection to information theory, I thought about this. If we're going to start bringing in entropy, need to have a way of justifying a connection between Bayes' theorem. Now, you can always substitute Bayes' theorem into Shannon's equations. Claude Shannon, the guy who invented information theory. And in fact, Leidesdorff did this in one of his papers. But why do we really want to do this? What's the justification for it? And I began to think about this, and I said, well, maybe there's an encoding and a decoding process that are sort of implicit in a theoretical framework, in a theory. So we have a theory right here, and let's say here's some pieces of evidence that are coming in. Is there an encoding process that's going to occur? And then is there a decoding process after that where we're going to predict new versions of those two pieces of evidence? And that seems to kind of make sense. So I thought about Kepler and all of the Mars observations that he had from Tycho. And Kepler took like a sample of his observations and said, well, maybe it's a circle. Maybe the orbit of Mars is a circle. He was trying to figure out what kind of shape does that orbit have. And he fixed his circles dimensions by using some of his observations. That's the encoding process. Then he predicted all the positions of those Mars observations in a decoding process, and he found out they disagreed. So it wasn't a circle. So he had to go back and say, well, what should it be? And he tried an oval, and the oval shape didn't work either. And eventually he hit on the ellipse, quite accidentally, actually. So that's an example. I think now maybe this applies more generally, maybe it doesn't. So I'm just throwing this out there as a speculative idea of how to justify applying information theory concepts. And of course, we all know about Shannon's entropy. Here we have a single random variable, the PT probability of, let's say you're flipping a coin, and the theory is that it's going to come up heads. Well, it could be a theory of, maybe it's a theory of relativity, and you're betting whether the theory of relativity is correct or incorrect. And if it's correct, let's say it's going to fall at this end of the probability scale. If it's incorrect, it's going to be down here, and that's kind of nice, because if you know something for sure, if you know that the theory of relativity is wrong, then your entropy is going to be lower. If you know it's right, your entropy is going to be lower. If you don't know, and you're right in the middle at this 0.5, it's going to be the maximum entropy of 1, and you have the least information that you could have. It's the highest uncertainty. Some people actually call it surprisal, which I don't particularly care for, but it's surprisal in the sense that you're surprised if you have a fair coin, it comes up heads, you're surprised. If it comes up tails, you're surprised. So I don't know if that's such a great word to use, but some people do. So you can also, in information theory, have something called conditional entropy. And I never tried this before, but I just plotted this out. What would be if I took my conditional or likelihoods, the probability of Evans given, not the theory probability, and I plotted that against entropy, and it gave you this nice sort of tent shaped figure, with the maximum being when the likelihoods are each equal to 0.5. So there's an analogy between, this is where you have 2 random variables, and the other one I showed you before was 1 random variable. It's very similar kind of outcome. And low entropy people associate with something that is concentrated on a few instances. And high entropy is something more uniform. And this goes back, there's a very close analogy between the information theory version of entropy and the physical Boltzmann entropy, as they call it, where you're talking about the distribution of states over a system of, let's say, gas molecules flying around. And you notice here that this conformation occurs over here on one side and conformation on the other side, and the shape depends on the prior probability that you assume. Now, there's a comparable information measure, information theory measure called mutual information. All these are different equations that Shannon came up with. And this one I sort of call my Batman figure because it looks sort of like a batwings here. And the interesting thing about this is that the mutual information is zero when the two likelihoods are equal. So like when we saw before, this is the state of not knowing whether you got confirmation or disconfirmation. So it's kind of a parallel to the Bayesian ideas. Now here, I'm not going to go into detail on this because I think I'm running out of time, but when I think about this stuff, I think about going through stages. First, there's one stage where you may have a theory and another theory it's competing with, and you have a piece of evidence, and you go to third version, and you pile up the evidence. As you do that, you're posterior, and you're feeding the posterior of one as the prior to the next step. That's how the Bayes theorem is supposed to work. And the posterior probability is going to go higher, assuming these pieces of evidence are being explained better by your theory over here on the left, and the entropy is going to go down. How I code my historical examples is using, this is probably the most controversial thing that I'm doing. How sure is a scientist that a theory leads to or explains or predicts the evidence? So I'm selecting a value from this grid where the theory and evidence are either strongly consistent, weakly consistent, neutral, which is my midpoint, inconsistent or strongly inconsistent. And it's more or less an arbitrary scale. I could have used other values and I would have gotten the same result. So if I'm dealing with somebody who's really biased against some piece of evidence or some theory, and I'm going to put them down here in the either strongly inconsistent or strongly consistent. So you can include people with biases, and that's not a problem. I'm going to only be able to probably talk about one of these diagrams. I have the continental drift theory in 4 different stages, or actually only 3, but there is a 4th one haven't done yet. You got Wegener's continental drift over here. That's actually when the continents are assumed to have been together and all glopped together at one point a few million years ago, and then separated out. They moved around. They floated to new locations. And the other theory is called the contractionist and permanentist theories. These are hard words to pronounce. The contraction is when the Earth is cooling and the crust is buckling. And the contractionists, like the American Dana down here, who was a staunch permanentist, he thought that was how mountains were formed. So the whole Wegener published his theory in 1912 and then wrote a book about it and went through several editions. He died in 1930 on the Greenland ice sheet. He froze to death. Many people were opposed to his theory. And I've tried to code in a consensual, trying to capture the consensus of opinion. Almost all of these pieces of evidence, the congruence of Africa with South America, the similarity of the fossil and fauna, the ancient glaciation in temperate regions like India had glacial deposits, the mountain range formation, all except this last one, the Newtonian explanation of why these continents move, will fit rather well together with either one of these theories. So when you calculate the posterior, you're coming up with a slight deficit for the Wegener hypothesis, as opposed to the permanentist and contractionist hypothesis, sort of lumped together, except for this one problem area here. And this was caused by a gentleman named, he was a physicist named Harold Jeffreys, who was staunchly anti-drift, because he said the Newtonian forces that are required to move continents are just too great. And Wegener is not, hypothesizing any strong forces, and he has these tidal drag thing and something else. So the theory really, this was the Achilles heel of this early theory. Harold Jeffreys turns out to be a pioneer in Bayesian analysis. He wrote a very influential early textbook on how to apply Bayes to scientific issues. Wegener said, the idea occurred to me looking at a map of the world. So this was very kind of seat of the pants science. He couldn't get a geodetic measurement, which would have sort of cemented his theory. He thought he saw one. He thought he saw Scandinavia and Iceland drifting apart, and he could measure it astronomically, but it turned out not to be a valid measurement. Many years later, this gentleman here, Edward Bullard, a British guy, claimed in 1964, when Wegener did his work, it was in the 1915 era. Bullard says the fit of the continental shelves is remarkably good, and he did that mathematically. So there's an example of how evidence can change. You can say, well, the continents, if you take the outline, they look a little bit similar, but they don't really fit that well. But Bullard said, I'm going to use the continental shelves, and lo and behold, a much closer fit. So that just goes to show you how evidence over time can shift and change the outcome of a theory. I'm going to stop here because if I continue, it'll go on for another hour. I've done, as I mentioned, 2 other case studies, one on DNA and one on the TRF model, following the case study of Latour and Woolgar. How am I going to do this in the future? I'm going to start with a specialty cluster that we create by citation analysis or some other method. I'm going to use reference and citation context and other text to identify theories and evidence, and I'm going to try to use artificial intelligence. I'm going to try to use the new versions of large language models that are now available, and do a fine tuning of those to identify my conditional statements. I'm going to average, or probably take the median for different authors in order to get a consensus version, a group consensus, and then I'm going to compute a group posterior. So that's how I'm going to combine. That's how I hope to do this in the future. I haven't quite gotten to that point. So this is very much a work in progress. I think that Bayes will eventually be applied to many other case cases in the history of science, and I think that it will be successful in giving people more insight into the discovery process and how resilience comes about in science. So thank you. These are the three sources that I used. Unbelievably good historical research. There's other books besides this, but these are the ones that I used in particular. And this Henry Frankel compendium of 4 volumes on the continental drift controversy is just a wonderful compilation. So thanks. Happy to answer any questions or complaints.
Thank you very much, Harry. You confirm that you hear us?
Let me just put my earphones on so I can hear you better.
Okay, great. And I think there are many questions, but I had no time before to introduce Harry Small. I think that everyone here is familiar with him, but he has been truly one of the fathers of scientometrics. He developed co-citation analysis and the idea of citation as a concept symbol. And he worked a lot with Eugene Garfield. He was chief scientist at IC. And so it's really an honor to have him here because, you know, it's like having a giant of scientometrics with us. And also, let me say that he has been one of the scientometricians that has been more in touch with philosophy of science, and especially with Kuhn's theory of paradigms. It was really great to be that he is with us. So first question, I think it's from Andrea.
Yeah, but I have to go out, so maybe somebody from the phone.
Let's start. So now the people with questions will come in here, and I will give them the microphone so that you can hear their questions. So please.
Okay.
Henry, thank you very much. It's Andrea here.
Oh, hi, Andrew. Good to see you. Long time.
Long time no see. You know, yeah. Okay, great seeing you. I was wondering if you see an application of these kind of deconstruction, reconstruction of scientific debates in actually teaching students about the history of a field.
Oh, yes. That's a great idea. I'm not in a position to teach anybody anything at the moment, but I think it is instructive to look at the evidence that's around, that's available for the competing theories. And I think this is a wonderful way of structuring actually a debate among different points of view. You look at the evidence that is shared or that could be shared by the different points of view, and it gives you a way of kind of weighting the decision. And of course, people can have vastly different opinions about whether some theory accounts for something or not. And that's, to me, the beauty of it, is that it allows you to take into account a diversity of points of view. A lot of philosophy of science, to me, doesn't allow you to do that, or not very easily. I'm probably misinterpreting that.
I could even imagine that you, if you support that by automatization, you could even make a game out of that. So letting people different kind of, letting them make their own estimates.
Yeah, I mean, what was very encouraging to me when I started, I did only one quick look at the OpenAI kind of platform, and you can submit training sets to it, and you can, or sometimes they call them fine tune, and then you can ask them to classify, and the classifications are much more accurate with the
Yes.
with the new generation of AI tools
Yes.
than they were for the classical tools. I mean, it's just no comparison. So to me, if I submitted a set of conditional statements, like sentences that were stating like the continental shelves for Africa and South America fit together, blah blah blah, and I had hundreds of such statements that was able to submit. It would be able to pick out the ones and probably even rate them by, degree of conviction. So I don't want to push this automation too hard. I think that we need to do more of the just sort of manual look at the data, try to figure out what it means. And then after we've done it manually, then go to the automation and see what that does and see if we can get any kind of agreement between what we have sort of our human judgment versus the machine judgment. So I don't know how it'll work out. Maybe it won't, but it seems to have the right flavor. The fit just seems to be,
I
correct.
also think that your instinct is right. In our institution, one of our research engineers, Slava Tikhonov, has played a kind of ping pong between large language models and has now also installed an OpenAI on the Surf infrastructure. And all his experimentation prove that the machine cannot replace the human. And if my engineers are saying that, that's really remarkable, yeah. And that actually the kind of the pinpoint between the structured data which we have also available. So if you think already classified data, so already think about knowledge organization systems, think about Wikidata. So if you kind of organize a dialogue between, we call it the librarian and the expert, yeah. So I will send you an email, bring you in touch, and maybe some of the infrastructure he has set up could be tested with your ideas. That would be wonderful.
Oh, great. We should be in touch.
Yes.
Okay, see ya.
Hi, Henry. Thank you for the talk. I wanted to ask you two things. So first of all, one comment. Your talk reminded me a lot of a new article from Patrick Grimm. I don't know if you know him.
Oh, no, I should.
He has this paper called Scientific Theories as Bayesian Nets, Structure and Evidence Sensitivity. And so, I mean, I understood that your perspective was more on the history of science to understanding theories and so on. But I think that the starting point is really the same. So maybe, I don't know if you knew it already, good, but otherwise I think it's worth taking a look probably. Because
yes.
So he does the same, what you did with Wegener's theory and contractionism and so on. He does it with the COVID-19 evidence in the present case, and he compares the theory of COVID being airborne or COVID not being airborne or something like this, and he tries to assign likelihood probabilities to each piece of evidence and see. So I think it's very similar. There's definitely something to look at them.
Yeah. I appreciate your recommending that, because it's very hard for you to find sort of papers that are analogous to what you're trying to look at, and particularly because Bayes is now used in biology and physics. And I can't.
That's definitely good. And then the other thing, I was more of a general question, maybe also beyond your scope, but I'm curious about it. So lots of philosophers have argued that the theory we subscribe to, the theory we adopt, also kind of shapes the evidence that we can find, right? So these two are not two completely different things, right? So if I subscribe to theory one, maybe I am more likely to see evidence one, whereas if I subscribe to theory two, evidence one is just less likely to pop up for me because I just subscribe to a different, well, I guess, system or something like this, right? And from what I got from your presentation, you haven't made this distinction. I was wondering if you were planning on doing it, if you think it's just irrelevant in your project, or yeah, any kind of thought about it. Thank you very much.
Yeah, that's a really, really good question. I mean, this whole business about evidence and how you find evidence that's relevant to a particular hypothesis is just it's like magic. I don't know how it, I was trying to think of how in whether in information science, for example, you used to talk about relevance judgments, is one thing relevant to another thing. And your statement about evidence, some pieces of evidence being more relevant to one theory than the other theory is right on target, because that's exactly like the congruence of Africa and South America, for example. That isn't very conciliant with the idea that South America and Africa never were together. I mean, it's almost like it's the only way you can explain that congruence. So it wasn't a welcome piece of evidence if you're, a contractionist or a permanentist to see that sort of evidence. So it's obvious that when evidence that comes in that favors your hypothesis, you're not going to embrace it. And I was going to mention one other kind of sideline here. This fellow Harold Jeffreys, who was this pioneer in Bayesian analysis, who was a physicist but an arch enemy of the drifters, as they call them. He refused to look at data that was in support of the drifting hypothesis. He was so biased in his outlook, it's almost embarrassing. And toward the end of the period, the 50s and the 60s, what happened was that new types of data entered into the picture, particularly magnetic data. And it turned out that magnetic data was the key to proving that continents actually drift. But some people, to the bitter end, refuse to even consider that as a possibility. So it's an interesting question about people's mindset. How can people be so wedded to a hypothesis that they refuse to consider other data, when obviously the other data is strongly supporting what you don't believe in? So it's a very important question, even in today's political atmosphere. How do you break down that barrier? I don't know. I don't know the answer, but it's really good. And then you have all the questions about the perennial question about being only wanting to seek confirming evidence, the confirmatory bias. That's another thing that enters in here. And, in Bayes, I think there's a danger of putting every little piece of evidence in. But because I'm using this naive Bayes model, if you have two pieces of evidence that actually are very positive of each other, the whole model breaks down. So that's another thought. But thank you for those ideas. They're really, really great.
Thank you.
Vincenzo?
Hi, Eric. I'm Vincenzo.
Hi.
I am a philosopher of science, and I'm also a Bayesian philosopher of science, so I cannot help commenting on the talk, which was very interesting. On the other hand, it's not so easy, so I will take just a little time to try to make the connections that I need. So yes, there is a story of Bayesian attempts to analyze case studies from the history of science, and I happen to be one of those who find that project still extremely interesting. But I have to say, I'm not very sure whether this is actually like a common approach to that. There are a couple of things that happened like along the way in that part of the story of general philosophy of science. That is, on the one hand, people have been, it is true that many philosophers of science nowadays would be happy to conceive that the Bayesian framework is a very powerful and flexible tool to represent, scientific, epistemic notions, because you have grades, you have degrees, you have beliefs, you have all kinds of very subtle tools. On the other hand, when you go to the history of science, there's always been a concern that you can basically tell whatever story you want. So you go back to, I don't know, the Copernican revolution, and then you can tell a story of a Bayesian route to go Copernican, or you can tell a Bayesian story with other numbers as a basis to resist like the revolution for a long while. Just by example. So that's one part of the problems, and then there is another part of this issue that actually you can trace, for instance, to Kuhn. So Kuhn at some point said something along the following lines. Yes, of course. The things that I say. In the case of Kuhn was arguably he had a very kind of descriptive agenda. Much more than others, let's say. And even then, though, at some point you find remarks of this sort. So, yes, I realize that a Bayesian can sort of translate many of the things that I say, right? I don't know, the paradigm, weights about virtues and whatever. And he had like a bit of he gave the impression to take all this exercise as not terribly enlightening as regards our understanding of real science happening, as it were. Okay, so I would like to say that your project actually can fly. I very much like this revival. I was just wondering, how do you feel about these more like classical challenges? Maybe the answer is about the technical tools that you can deploy in order to fix numbers. I don't know. I'm not I have no technical proficiency in the scientometrics research at all.
Yeah, I haven't really succeeded in connecting it to scientometrics. So I don't want to give you any false impression here. But I do see a road to the connection, but it will be more than just scientific published papers and more than just citations. It will have to include the full text, and it'll have to include the consideration of language models and the rest of it. Now, one of the points that you made is very important, and that is that it's implying Bayesian ideas to these historical examples. You can definitely jigger the numbers, so to speak. You can fix things so that Copernicus looks mighty good and Ptolemy doesn't look so good, or vice versa. So particularly in these cases where there's a very close, there's very little evidence to say that one is better than the other, or when you look at, I've read up on this, on the Copernican Ptolemy thing, and it's sort of mind-blowing how little difference the Copernican model made in predictions and other things. Some people have actually said that Ptolemy was much better than Copernicus. And when you get to some of these older examples, and I think that's why I'm glad I didn't start with Copernicus or even Kepler, and that I start doing more contemporary examples, because there's just not enough information available on people's attitudes. And that's what you really have to get at is, I don't think it's so important to decide whether Copernicus was better than Ptolemy or vice versa. I think it's important to lay out the pieces of evidence that were being used and at people's attitudes toward the evidence given the theory. I think that just laying that out is very useful and not necessarily knowing that is this a 0.6 or a 0.5 or a 0.3, you know, the actual numerical translation of that degree of certainty is probably not that important. And to me, that's why I call this qualitative Bayes, because there's an element of judgment that has to enter in here that you can't do without it. You have to have some degree of judgment, and people can have different opinions about, you know, particularly for historical examples. But I don't know if that any of it is a sort of a flexible framework. But that part of it I actually kind of like, because that allows people to discuss things, debate them, and say, well, if you look at it this way, he really meant that, or he meant that. Although that's why I like taking contemporary science examples, like cold fusion, for example, because we'll have a good deal of information about people's attitudes toward that, and whether it's diaries or emails or whatever, you know, what other kind of information we can bring to bear, I think that will be important. So, yeah, I don't know whether the automation of this is going to work in principle or not. I have a hunch that it might, because those new tools are very powerful. And if it can help us, if it can give us a leg up on collecting the data and analyzing it, that'll be an amazing thing. So thanks. I can't answer those questions very easily, but I appreciate your asking.
Thank you. Thank you so much.
Please.
Yeah, thanks for the talk. It was very interesting. So I have a question about the automation you were talking about. I hope I understood everything correctly and my question makes sense, but I was wondering whether you can get even more out of your Bayesian approach once you start aggregating like the judgments of many people, because then you can get a hierarchical structure in your model, or like have a prior that is properly a distribution with like the standard deviation in it as well. Like, have you thought about those kinds of things already? And do you think it might make sense to do it like that?
Yeah, I do think that makes sense. And what we really need is a sampling, or you know, as complete a set of opinions from the people in the field as we can get. And one of the things that I like about Henry Frankel's 4-volume book on continental drift is that he has raw data on transcripts of interviews with scientists. And I think they will be very, very important, because those firsthand accounts are really, really necessary. Of course, the problem is that you just don't go to some guy on the street and ask him, are the continents moving? You have to restrict your questioning and your data collection to people who might have some expertise. So that's a problem. But generally speaking, we're not going to have that kind of public opinion anyway. You know, that's not going to be available for historical cases or even contemporary cases. But if you get to global warming or you get to climate change, yeah, you could ask the man on the street. In fact, I think people have already done that. So that's another example that would be fun to do. Look at the scientific evidence for and against climate change. Of course, there's not much of a contest there anymore, is there? So you kind of know what the answer is going to be. So that's why I thought it would be a good idea to look for something that was disproved, or, you know, quote unquote disproved, a failure of a theory rather than all these success stories. So that's something that I think hopefully I'll have a little more time left to devote to this, and I will do that. But the automation of it, I think there's two challenges. One is that we need to automate the differentiation of theories and evidence. And it doesn't mean evidence can't be theoretical. In fact, in my example from continental drift, I was using Newtonian force considerations as a piece of evidence. So a theory can be an evidential unit if the theory is well established, not if a theory is totally speculative. But so theory and evidence distinction, and then the bringing together of theory and evidence with some sentiment analysis on top of that, say how likely or how strongly rather the opinion is. So if somebody says, well, maybe Africa and South America look a little bit alike, but I don't really think so. That's a pretty lukewarm endorsement. You want to know, you want to be able to tell from a sentiment analysis standpoint, which is something they can do with the new systems, how strong convictions are regarding these conditional statements. So those are the kind of the challenges that I think the AI end of this is going to face. Anyway, thank you.
One last question.
Hello, Henry. This is Chao Mei.
Jay, I knew you would ask. I assume that you've already done everything I'm talking about, right?
I was hoping to meet you face to face here.
Yeah, I was hoping to, but just things didn't work out. I'm so sorry to miss you.
Yeah, your talk got me thinking several things. We're coming from about uncertainty, that's one, and then the
Yes.
structure of the network,
Right.
the context that could be embedded, and also how I would envisage it could be changing over time, and some part of network could collapse altogether and
Yes.
forgotten or replaced.
Yes.
So also in terms of automation, I think one thing will be fascinating if you have the network as the inference engine, then you could do lots of things with it. You can see according to the state of the knowledge based on this encoded structure, whether you have something new or something fundamental. So I was thinking, let me put it the other way. What sort of time frame for this knowledge that is consolidated into one of these, like what I call a snapshot, maybe like
Yeah.
10 years
Yeah.
or, yeah. And
Yeah.
how will that change if I can ask you to put a handle on it? Can we crank forward and backwards and see the history replay or to see the contribution of specific contributions? How would that change those kind of structures? I mean, it got me thinking a lot of these kind of things, but it's fascinating. Thank you.
Yeah, you're absolutely right. Yeah, the time frame, it's interesting. These are not equal time frames because the original Wegener continental drift theory was fairly static from 1915 when that book was published up to roughly 1950. So you're talking about a 30-year period or whatever where not a whole lot changed. I mean, the evidence didn't really change that much. The theory didn't change a whole lot. There were people who made little suggestions about how to improve the theory. but nothing that's substantive. So, and the next phase is where people started measuring the magnetism. I didn't get to this in my talk, but there's another phase where they were looking at what is the magnetic direction of rocks on different continents, and why don't they all point to the North Pole? So and that the so-called directionalists and they would go around with magnetometers and measuring rocks on on different continents, and that period was about 10 years. You know, I mean, it continued after that, but so that's like 1950 to 1960. 1960 marks another shift from 1950, let's say, to 1970, where the oceanography was the dominant force, and people were dragging magnetometers under on the seafloor across different structures in the seafloor to measure what they call magnetic reversals. And those magnetic reversals were the key to really, and I didn't get to this, but it's almost like an aha sensation moment where you say, oh my gosh, this data really fits. The magnetic striping, so-called, on either side of one of these ocean ridges was symmetric, and it was on a time scale that was identical to the magnetic reversals in core samples that were obtained by drilling. So that confluence of information from the coring and the oceanography vessels, particularly from all different institutions, Scripps and Lamont in New York and so forth, that confluence really cemented the position of continental drift, and it became in the next decade. So there's like three different eras that correspond perfectly to Henry Frankel's volumes, a 4-volume work. The first one is about Wegener. The first volume is Wegener's theory up to about 1950. The next one is about the magnetic directionalists. That's the 50s. The 60s was the oceanographic measure of the reversals, and the next period, let's say the 70s, was plate tectonics and the mathematization of the whole thing. So once you got to that point, it's a whole different ballgame. There's precise measurements that people were making, and they actually measure how far Greenland had gone from Scandinavia, but it only was like a quarter or an inch or a half an inch a year. So it was too small to see astronomically. So these are the periods, and yeah, I'd love to be able to do things with that network, like a simulation and of a time simulation. The one thing I did notice, and this is something that I think will be important when we start talking more about entropy. If you have a theory which has a bunch of lines coming out of it, where each line is getting weaker, and you have another theory over here where the lines coming out of it, and those lines are getting stronger, at some point you're just going to have to say, forget it. We're just going to forget about that contractionist theory and the permanentist theory. Just drop off, and just you're left with the continental drift of the plate tectonics. And so that's what I think is going to happen. And when you get that kind of imbalance in a network, I think that's the entropy measure that we're looking for.
Yeah.
But anyway, I look forward to talking to you in Philadelphia.
Yeah, I'd like to see some, yeah, very, very short. Okay, I'd like to see some examples like I studied mass extinctions.
Yes.
They have some specific event, like diagnostic evidence.
Uh-huh.
So it have before and after that, and you can see how suddenly the network could change. Right.
Yeah.
That's you're still looking for a case. But anyhow, thanks so much.
Okay, thank you.
So, thank you very much to Harry Small, and so people are clapping their